In the autumn of 1945, as Europe began to emerge from the shadow of the Second World War, a small team of French engineers embarked on a mission that would reshape their understanding of modern warfare and rocket science. These men had a singular objective: to dissect, analyze, and understand the most sophisticated weapon ever deployed during the conflict. The weapon was the German Vergeltungswaffe II, known to the world as the Phase II rocket. What they discovered would not only reveal critical vulnerabilities in this marvel of engineering, but would also lay the groundwork for France's future in space exploration. The story begins not in France, but in the final desperate months of the Third Reich. By September 1944, Germany was losing the war on all fronts. The Allied forces had successfully landed at Normandy, Soviet armies were pushing westward, and the strategic bombing campaign was devastating German cities. In this atmosphere of impending defeat, Adolf Hitler placed his hopes in what propaganda minister Joseph Goebbels called wonder weapons. Among these, the Phase II rocket stood as the most technologically advanced and terrifying. The V-2 was unlike anything the world had seen before. Standing 46 feet tall and weighing over 28,000 pounds at launch, it was the world's first long-range guided ballistic missile. Powered by a liquid propellant rocket engine burning a mixture of ethanol and liquid oxygen, it could reach speeds of over 3,500 miles per hour, traveling at supersonic velocities that made interception impossible. The rocket could climb to the edge of space, reaching altitudes of nearly 60 miles, before descending on its target with devastating force. The weapon carried a 2,000-pound warhead filled with amytal high explosive. When it struck, there was no warning. Unlike the earlier V-1 flying bomb, which announced its arrival with a distinctive buzzing sound, the V-2 traveled faster than sound itself. The first indication of its presence was the explosion, followed seconds later by the sound of its supersonic passage through the atmosphere. This psychological terror was precisely what Hitler and his commanders had intended. Development of the V-2 had begun more than a decade earlier, rooted in the work of German rocket enthusiasts and engineers. The man who would become synonymous with the program was Wernher von Braun, a brilliant young engineer who had been fascinated by spaceflight since childhood. In the early 1930s, von Braun joined the German Army's rocket development program, bringing with him dreams of space exploration that would be twisted into weapons of war. The program moved to Peenemünde, a remote facility on the Baltic coast, where von Braun and his team worked on a series of progressively more advanced rockets designated as aggregate or A-series. The A-1 and A-2 were early experiments. The A-3, tested in 1937, was a failure, plagued by control and aerodynamic problems. But these failures taught invaluable lessons. The team pressed on, and by 1942, they had developed the A-4, which would become the V-2. On the 3rd of October, 1942, the first successful A-4 test launch took place at Peenemünde. The rocket soared to an altitude of nearly 60 miles and traveled 125 miles downrange. Walter Dornberger, the military commander of the program, reportedly declared that day as the beginning of a new era in transportation and space travel. But the dream of space exploration would have to wait. Germany needed weapons, and the A-4 would become the V-2, a tool of vengeance. The path to production was anything but smooth. The rocket was immensely complex, representing the cutting edge of multiple technologies. The guidance system relied on gyroscopes to maintain stability and trajectory. The engine required a turbopump capable of delivering over 8 tons of fuel per minute to the combustion chamber. 4 graphite vanes positioned in the engine's exhaust stream provided steering during the powered flight phase. All of this had to work perfectly under extreme conditions, with the rocket subjected to intense vibrations and temperatures. In 1943, as production began, the Germans encountered a crisis. Early production missiles suffered from an 80% failure rate. Rockets would explode shortly after launch or disintegrate in flight, or veer wildly off course. The problems had multiple causes. The manufacturing process, rushed and complicated, introduced inconsistencies. The guidance systems were sensitive and prone to malfunction. The structural components, pushed to their limits, sometimes failed under stress. It would take until November 1944 before the final fixes were implemented in the production line. Even then, the V-2 remained a weapon of questionable military value. The circular error probable, a measure of accuracy defining the radius within which 50% of shots would impact, was approximately 4.5 kilometers in testing. In actual combat conditions against London, this increased to 12 kilometers. This meant that the V-2 was essentially a terror weapon, capable of striking a city, but not a specific military target. The British conducted a clever disinformation campaign to further degrade the weapon's effectiveness. Nazi agents in Britain, who had been captured and turned, fed false information back to Germany about where the rockets were actually landing. The Germans, believing their rockets were overshooting London, adjusted their aim to what they thought was the city center, but was actually the less populated countryside of Kent. This deception saved countless lives. Despite its limitations, the V-2 killed thousands. Between September 1944 and March 1945, over 3,000 V-2 rockets were launched. London was struck by over 500 rockets, killing approximately 2,700 civilians and injuring more than 6,000. Antwerp, the vital port supplying Allied forces, received even more intense bombardment. The rocket's psychological impact was profound, a weapon from which there was no defense, striking without warning from the sky. As Allied forces advanced into Germany in early 1945, a race began. The Americans, British, French, and Soviets all recognized the value of German rocket technology and the scientists who had created it. Intelligence teams scrambled to find and secure V-2 components, technical documents, and most importantly, the engineers themselves. The Americans moved first. On the 10th of April 1945, Combat Command B of the United States 3rd Armored Division entered Nordhausen in central Germany. There they discovered the Mittelwerk, the underground factory where V-2 rockets had been mass-produced using concentration camp labor. Inside the tunnels, American soldiers found railway cars loaded with completed rockets and thousands of components. Colonel Holger Toftoy of Army Ordnance immediately organized Special Mission V-2 to secure this treasure trove. Over the following weeks, American forces collected approximately 300 railway cars worth of V-2 parts and shipped them to the United States. The British, meanwhile, organized Operation Backfire. With American consent, they assembled components sufficient to build 8 V-2 rockets. The operation was led by Major General Alexander Cameron, and the launch site chosen was the Altenwald Naval Gun Testing Ground near Cuxhaven on the North Sea coast. The British goal was not simply to possess the technology, but to thoroughly understand it. They would assemble and launch the rockets themselves, with German personnel providing guidance and technical assistance. The task was enormous. Assembling a V-2 rocket was not like assembling a conventional weapon. It required specialized equipment, trained technicians, and careful procedures. The British searched throughout their occupation zone for missing components. Some 400 railway cars and 70 Lancaster bomber flights were needed to transport 250,000 parts and 60 specialized vehicles to Cuxhaven. The most difficult items to find were the electrical batteries needed to power the guidance gyroscopes. German prisoners of war and civilian technicians were recruited to assist. Most came willingly, seeing an opportunity to continue their work and demonstrate the technology they had labored so hard to create. Among them were experts in propulsion, guidance, fuel handling, and launch procedures. Under British supervision, they began the painstaking process of rocket assembly. On the 2nd of October, 1945, the first backfire rocket was launched successfully. The missile climbed into the sky and arced out over the North Sea, impacting near its intended target with remarkable accuracy. 2 days later, a second launch took place, though this one experienced an engine failure shortly after liftoff and crashed into the sea. A third and final launch occurred on the 15th of October, designated Operation Clitterhouse, conducted as a demonstration for representatives from the United States, France, the Soviet Union, and the press. The backfire launches were filmed, and the footage would become iconic, often mistaken for wartime German footage because the personnel wore their original uniforms and the rockets were painted in their original camouflage scheme. More importantly, the launches generated extensive technical data. British engineers meticulously documented every aspect of the rocket's assembly, fueling, and launch procedures. This information was compiled into a 5-volume report that would be shared with the Americans and, to a limited extent, with the French. While the British conducted their tests, the French were pursuing their own acquisition of German rocket technology. In October 1944, even before the war's end, France had established GOPA, the operational group for guided missiles, specifically to gather intelligence on German advanced weapons. Under GOPA's authority, Henri Moreau was appointed head of CPA, the Center for the Study of Self-Propelled Missiles, with the mission of potentially putting the V-2 into production in France. Between May and September of 1946, CPA recruited approximately 30 German engineers who had previously worked at Peenemünde. Among the most significant was Wolfgang Pilz, a propulsion specialist who had worked on the V-2 engine development. These engineers, along with their families, were settled in Vernon, a town halfway between Paris and Rouen. There they would form the core of France's nascent rocket program. The French engineers who would work alongside these Germans were a diverse group. Some were military engineers who had served in the war. Others were civilian scientists and technicians drawn from French industry and academia. Many had engineering backgrounds in aircraft design, artillery, or chemistry. What united them was curiosity and a recognition that rocket technology represented the future of both warfare and, potentially, peaceful space exploration. The French faced a significant challenge. Unlike the Americans, who had secured entire rockets and large quantities of components, or the Soviets, who had captured the Peenemünde facilities and later Nordhausen after the Americans departed, France had relatively limited access to hardware. They acquired some V-2 components from suppliers in France and from the French occupation zone in Germany. However, they found that approximately 75% of the parts needed to assemble complete V-2 rockets could be obtained, but the remaining 25% were unavailable due to American and Soviet refusal to supply them. This limitation forced the French to adopt a different approach. Rather than simply copying the V-2, they would need to thoroughly understand its design, identify its principles and its flaws, and then develop improved versions. This analytical approach would prove invaluable. The French engineers, working closely with their German counterparts, began a systematic examination of the V-2's design, component by component, system by system. The analysis revealed a weapon that was simultaneously a triumph of engineering and a catalog of vulnerabilities. The French engineers started with the propulsion system, the rocket's heart. The V-2 engine burned a mixture of 75% ethanol and 25% water, combined with liquid oxygen. The choice of ethanol and water as fuel was itself a compromise. Pure alcohol would have been more efficient, but Germany's alcohol production was needed for other war purposes, and the water addition helped cool the combustion chamber. The engine generated approximately 27 to 28 tons of thrust, an impressive figure for the time. However, This power came with significant engineering challenges. The fuel and oxidizer had to be delivered to the combustion chamber at extremely high rates. Over 8 tons of propellants needed to be pumped in just 6 to 7 minutes of powered flight. This required a turbopump of extraordinary power and reliability. The turbopump assembly was identified by the French engineers as one of the rocket's critical vulnerabilities. This unit, weighing 450 kilograms, consisted of 2 pumps, mounted on a common shaft, driven by a steam turbine, producing 675 horsepower. At full power, the pumps rotated at 5,000 revolutions per minute. The steam to drive the turbine came from a generator where hydrogen peroxide and calcium permanganate were mixed, producing a chemical reaction that generated superheated steam at over 400 degrees Celsius. The French engineers discovered that this turbopump was the V2's Achilles heel for multiple reasons. First, it was incredibly difficult to manufacture. Only one factory in Austria, at Jenbach, could produce these turbopumps with sufficient precision and quality. Any damage to this single facility would have crippled V2 production. Second, the turbopump was subject to immense stress during operation. The high rotation speeds, extreme temperatures, and corrosive propellants meant that even small manufacturing defects could lead to catastrophic failure. Third, the unit was highly sensitive to vibration. If the rocket experienced unexpected oscillations during launch, the turbopump could fail, leading to engine cutoff or explosion. Moving their attention to the combustion chamber, the French engineers found another area of vulnerability. The chamber had to withstand temperatures approaching 1,700 degrees Celsius while maintaining structural integrity. To manage this heat, liquid oxygen was circulated through ribbed tubes along the outer wall of the chamber before being injected into the combustion zone. This regenerative cooling system was elegant but problematic. Any blockage in the cooling passages, any crack in the chamber wall, any imperfection in the welds could lead to burn-through and explosion. The injection system posed its own challenges. Fuel and oxidizer had to be vaporized under pressure by injection nozzles and delivered to the combustion chamber in precisely the right mixture ratio. If the mixture was too rich in fuel, combustion would be incomplete and inefficient. If too much oxidizer was present, the chamber could overheat. Getting this balance right required precision manufacturing of the injector components, something that was difficult to maintain in wartime production conditions. The guidance and control systems revealed perhaps the most sophisticated vulnerabilities. The V2 used a gyroscopic platform to determine its orientation in space. This platform, developed by the German company Kreiselgerät, was a marvel of precision engineering. 3 gyroscopes sensed the rocket's motion in pitch, yaw, and roll. A simple analog computer processed these signals and commanded corrections through the control system. The control system itself was unusual. During powered flight, steering was accomplished by 4 graphite vanes positioned in the engine exhaust stream. These vanes, each about the size of a dinner plate, deflected the exhaust flow to produce corrective forces. They had to withstand the rocket exhaust's extreme temperature and velocity while remaining responsive to guidance commands. After engine cutoff, external aerodynamic fins provided some stability during the ballistic phase, but the trajectory could no longer be significantly altered. The French engineers identified multiple vulnerabilities in the system. The gyroscopes were delicate instruments requiring careful calibration. They were sensitive to vibration, temperature changes, and electrical interference. The analog computer, while sophisticated for its time, had limited capability and no redundancy. If any component failed, the rocket would likely veer off course. The graphite vanes eroded during flight, and excessive erosion could compromise control authority. Manufacturing inconsistencies in the vanes could lead to asymmetric forces and trajectory deviations. The structural design of the rocket presented another category of vulnerabilities. The V-2's body consisted of a lightweight metal framework covered with thin aluminum alloy skin. This monocoque structure was efficient in terms of weight, but highly susceptible to manufacturing defects. Variations in skin thickness, imperfect welds, or damage during handling could create weak points. Under the stress of launch and supersonic flight, these weak points could lead to structural failure. One of the most significant problems discovered through analysis was the phenomenon the Germans called Luftzerleger, or airburst. A substantial number of V-2s, perhaps 15 to 20%, would disintegrate during re-entry. As the rocket fell back through the atmosphere at supersonic speed, aerodynamic forces and heating would stress the structure. If the rocket's angle of attack was wrong, if there were structural weaknesses, or if the skin had been damaged, the vehicle could break apart explosively. The French analysis revealed that this was partly due to manufacturing inconsistencies and partly due to fundamental design limitations in the nose cone and forward fuselage. The French engineers also examined the operational vulnerabilities of the V-2 system. A complete launch battery required extensive support equipment. The Mailerwagen, a specialized trailer, was used to transport and erect the rocket. A Vidalwagen carried the warhead. Additional vehicles transported fuel, liquid oxygen, compressed air, electrical ground support equipment, and launch control systems. Setting up a launch site required hours of work by trained personnel. The liquid oxygen, in particular, was problematic. It had to be produced on-site or transported in special dewars, and it was constantly boiling off, requiring top-off just before launch. All of this complexity made the V-2 system vulnerable to interdiction. Allied intelligence, British in particular, had worked tirelessly to identify launch sites, supply depots, and production facilities. Bombing campaigns had targeted these locations throughout 1944 and 45. The Germans had responded by adopting mobile launch tactics, firing from forested areas and moving frequently, but this only partially mitigated the vulnerability. Perhaps most damning was the analysis of the weapon's strategic effectiveness. The French engineers calculated that each V-2 rocket cost approximately 100,000 Reichsmarks, equivalent to over £2 million in modern currency. This was an enormous expenditure for a weapon with such limited accuracy and reliability. The entire V-weapons program, including both V-1 and V-2, had cost Germany the equivalent of about $500 million, comparable to the American Manhattan Project that produced the atomic bomb. For this investment, Germany received a weapon that killed approximately 2 people per rocket, a shockingly poor return compared to conventional bombing. The French analysis also revealed interesting details about German countermeasures against Allied efforts to disrupt the program. The massive concrete bunkers at Watten and Wizerness had been intended as bomb-proof facilities for rocket assembly and launch. These structures, particularly the dome at Wizerns, with its 5-meter thick concrete roof, represented an enormous investment in resources. However, Allied bombing had prevented their completion or rendered them unusable. This demonstrated another vulnerability. The concentration of effort on fixed sites made them lucrative targets. The shift to mobile launches had come too late to make a strategic difference. Through their systematic analysis, the French engineers compiled a comprehensive understanding of the V-2's vulnerabilities. They organized these into several categories. There were design vulnerabilities, inherent limitations in the rocket's engineering that could not be easily fixed without major redesign. Manufacturing vulnerabilities arose from the difficulty of producing components with sufficient precision and consistency under wartime conditions. Operational vulnerabilities stemmed from the complex logistics and support requirements. Strategic vulnerabilities related to the weapon's cost, accuracy, and questionable military utility. Armed with this knowledge, the French began developing what they called the Super V-2 program. Between 1946 and 1948, French and German engineers worked on designs for 4 variants of an improved rocket, designated R1 through R2M. These would progressively incorporate solutions to the vulnerabilities identified in the original V2. The R1 would have a stronger structure, a more reliable turbopump, and improved guidance. The R2 would introduce new propellants, liquid oxygen, and kerosene to increase efficiency. The R2S would add a turbopump-fed engine for greater power. The R2M would be a 2-stage design with a detachable booster and aerodynamic lift surfaces, giving it intercontinental range. The Super V2 program was ambitious, perhaps too ambitious. It called for rockets capable of ranges up to 3,600 kilometers, essentially French versions of the proposed German A9A10 America rocket that had never been built. However, the French government showed little enthusiasm for funding such an expensive program. France was recovering from the war's devastation. Resources were limited, and priorities lay elsewhere. In 1948, the Super V2 program was canceled. But the work was not wasted. The research and analysis were redirected toward a smaller, more practical project, the Veronique sounding rocket. This research rocket, named after a popular French song of the era, would become the first liquid-fueled research rocket in Western Europe. Drawing on the lessons learned from V2 analysis, the Veronique incorporated improved turbopumps, better guidance systems, and more reliable structures. It would fly successfully from 1950 onward, carrying scientific instruments to altitudes of over 300 kilometers. The French engineers who had analyzed the V2 went on to play crucial roles in France's space program. The Veronique would lead to the Diamant rocket family in the 1960s, making France the third nation to achieve independent satellite launch capability. The analysis techniques and engineering insights gained from studying the V2's vulnerabilities informed the design of these later rockets. The turbopump technologies, guidance systems, and structural approaches all benefited from the detailed understanding of what had gone wrong and what had gone right with the German V2. The legacy of this analysis extended beyond France. The technical reports produced by French engineers were shared to varying degrees with other nations. The identification of the V2's vulnerabilities became part of the collective knowledge that informed post-war rocket development worldwide. When American engineers developed the Redstone missile, essentially an improved V2, they benefited from understanding these vulnerabilities. When Soviet engineers built their R series of rockets, they too incorporated lessons learned from analyzing the German design's weaknesses. The story of the French engineers and the V2 analysis is ultimately a story about the nature of technological progress. The V2 represented a genuine breakthrough, the world's first space-capable vehicle, the ancestor of all modern rockets. But it was also a weapon developed under enormous pressure, rushed into production before its problems were fully solved, manufactured using slave labor under terrible conditions, and deployed in a lost cause. Its technological sophistication could not overcome its fundamental vulnerabilities. Those vulnerabilities were both technical and strategic. The technical problems, the fragile turbopump, the sensitive guidance system, the structural weaknesses, could in principle be solved through better engineering and manufacturing. The strategic problems, the weapon's inaccuracy, its enormous cost, its limited military impact, raised deeper questions about whether such a weapon made sense at all. The French engineers understood both aspects. Their analysis was thorough and honest, acknowledging both the V2's achievements and its failures. They recognized that the rocket represented both a marvel and a mistake, a technological triumph that came at an unconscionable human cost and yielded little military benefit. Their work helped ensure that future rockets would be better engineered, more reliable, and hopefully dedicated to more constructive purposes than raining terror on cities. As the French engineers completed their analysis in the late 1940s, the world was entering a new era. The Cold War was beginning, and both the United States and Soviet Union were rapidly developing ballistic missiles based on German technology. The arms race that would dominate the next 4 decades was taking shape. But alongside the military developments, space exploration was becoming a reality. The same technology that had been twisted into weapons of war was being turned toward peaceful purposes. The French contribution to this transformation was significant. By methodically analyzing the V-2's vulnerabilities, by understanding what made it fail as often as it succeeded, French engineers helped advance the state of rocket science. They learned that complexity was a vulnerability, that redundancy was essential, that testing and quality control could not be rushed, that systems had to be designed not just for peak performance, but for reliability. These lessons were hard-won. They came from studying a weapon that had killed thousands, that had been built by concentration camp prisoners working under horrific conditions that represented some of humanity's worst impulses, alongside some of its most impressive technical achievements. The French engineers had the wisdom to separate these aspects, to extract technical knowledge while acknowledging the moral dimensions of their subject. Today, when a European Space Agency rocket launches from French Guiana carrying satellites into orbit, its lineage can be traced back through the Ariane, through the Diamant, through the Veronique, to the work done by French engineers analyzing the German V-2 in the years immediately after the Second World War. That lineage is complex and troubling, a reminder that technology is neither good nor evil in itself, but depends entirely on how humans choose to use it. The critical vulnerabilities revealed by the French analysis became the foundation for solutions. The fragile turbopumps led to more robust designs with better bearings and materials. The sensitive gyroscopes evolved into inertial navigation systems with redundancy and self-checking. The structural problems prompted the development of better quality control and non-destructive testing methods. The guidance system limitations drove innovations in computing and control theory. Each vulnerability identified became an opportunity for improvement. In the end, the story of French engineers analyzing the German V-2 rocket is a story about human ingenuity applied to understanding, improving, and ultimately transcending a weapon of war. It is a story about how detailed technical analysis can reveal both strengths and weaknesses, how knowledge can be extracted from even the most troubling sources, and how that knowledge can be redirected toward better purposes. The V-2's legacy is complex, but thanks in part to the work of French engineers in the 1940s, that legacy includes not just destruction, but also the opening of space to human exploration. The critical vulnerabilities they revealed were not just problems to be fixed, but lessons to be learned about the importance of reliability, the value of thorough analysis, and the necessity of using technology wisely.